Hello everyone, this is a short instructional video how to use the seasonal operational option of the WEB.BM model. WEB.BM stands for Web Basin Management. The first thing you need to do is type www.riverbasinmanagement.com. Once you have it typed in your Google Chrome, you will get this login prompt. Now, in case you never logged in before in your life, you're going to have to click on register an account. To register an account, you need to enter your email address and some password, which doesn't have to be the same as the password you normally use to access your email. I'm saying this because people feel nervous about putting passwords in, although nobody can see your password here, myself included. But the reason for this is that we had to safeguard the model from somebody writing a script and opening 100 million user IDs. Once you put in your email address here, a link is going to be sent to your email. And you have to click on the link in order to activate your account. That's the only reason why you need an email address to open an account. If you already have an account, you simply go back to the login and you'll be typing your email address first. It doesn't have to be your email address that you normally use. You'll have to type in the same password you typed before. The first thing you're going to see when you log in is a list of your projects. Now, if you're a first-time user, this list is going to be empty. And in the case of the Bow River Management, the three district managers are going to receive a backup file which will allow them to restore this project. The way to restore the project is to simply click on this restore command here and use this option to overwrite the existing components. And even though you don't have components, just use it for now, please. And then choose the file that you will receive in email. It's going to be a zip file. After you click on the file in your email, click on the upload command here, and the project will be restored. It'll take a few minutes. Let's now click on this project. What you see is a list of nodes and channels that form this project. These nodes and channels are interconnected. We can exclude the existing nodes from the project or include the new nodes if we just manipulate the selection in the checkbox. The next thing would be to click on the map, because it's always easier to look at projects visually, and you will see something you're familiar with. This is Google Maps, and the entire project is shown as a layer in Google Maps. If you click on the satellite option, a lot of people think this is fancier, but I personally find it less productive. As they say, you can't see the forest from the trees. So I'm finding that this map option with the terrain selection actually works better. Our system starts from the Ghost Dam. It goes down through the Beresford Dam. It picks up Jumping Pound Creek as a tributary. And then right at the city, there is the Elbow River tributary. There is some diversion from the Ghost Dam just immediately below the Ghost Dam for the city of Calgary, and there are some other water licenses which are split here between junior and senior along every major river reach. But here you see the WID diversion. Modeling of this diversion was a bit tough because of the way the license was originally written. So we came up with something that looks like this, where for a low flow you're allowed to divert only 11.2 cubic meters per second. Medium flow, for which we selected average flow for the year, that's roughly 90 cubic meters per second. Maximum diversion for that is 16.8 cubic meters per second, and then for anything flowing in the river above 135 cms, we were able to divert the full capacity, canal capacity, which is 21 cubic meters per second. You can use this Google Maps interface to either look at the input data or to look at the results. If, for example, you want to look at the input data, then we can select any of these blocks, for example, or any of the reservoirs, right click on it, and click on the edit button. With this, the component is found in the list of consumptive use nodes. The model recognizes this as a consumptive use node, which is an irrigation block. It finds it in the list and it opens it up, such that if you wish to use this water use button and click on the custom selection here, you can see all 89 years of weekly water demands for this block. In the winter, between day 1 and day 8, which is the first week of January, of course it's 0, but as you go down a little more, you'll see that the demands kick in sometime around day 120, which is at the beginning of May. The data that were used here were all obtained from Alberta Agriculture. Before you can use the Google Maps interface to view the results, you should be first running the model and getting some sort of solutions. For that, you will go to this solver option in the top main menu, and in the solver option, you will select the project to run, and you will select a scenario. There can be more than one scenarios in a single project. So the project is a set of physical components that are interconnected, and the scenario are the instructions. The scenario contains instructions how to operate the components within a particular project. You have many ways to operate a system, and each scenario specifies one of those ways. In this case, you see only one scenario in the list, which was made to simplify things here. But now, if I went to run the calculate button immediately, I will get a simulation for all 89 years. Which is not what I want. I want to instruct you how to run the model for the next 10 weeks. And for that, you need to use this seasonal operational option. We need to fill these 4 boxes in order to do this. The first thing we need to tell the model is what's the date when we are running this. Today's date is normally you'll be using the date of the day when you're running the model. Here we're doing a little demo, so I'm going to go a little further than May. Let's say I'll pick 24th of June. Imagine we are at at this date today. How many weeks do we want to look ahead with the model? Typically, it could be between 10 and 12 weeks because we have a seasonal flow forecast for 3 months coming from another model. That model, if you remember, if you saw the previous video, gave us for this year 0.68, and we should enter the aridity factor here of 0.68 for this year. I'd like to show you something a little more drastic and how the model becomes helpful. We can assume that we have a 20 percentile year, which is 1 in 5 dry year. And we can also assume that we have uncertainty, which is 10% that's related to this prediction. So it could be plus minus 10% wrong. That will create automatically 3 scenarios, one being at 10 percentile, one being at 20 percentile, and one being at 30 percentile. When we now run the calculate button, the first thing that the model does is it scans our database of 89 years, and it pulls up all the data that we need to change dynamically for a short-term run. What is the first thing we need to change? Well, we need to put in the current reservoir levels. You can change them one by one by clicking on the selection here or here, and by clicking on the edit button, and then by putting in your value. And don't forget to click on the update button if you do that. But it's easier and more productive if you already have this ready in a separate file. So you can just click on copy, and you can paste the current reservoir levels by clicking on this paste from clipboard. You have to make sure though that in your spreadsheet all the reservoirs are listed exactly in the same order as they're listed here. But it's not too hard to get that order, because if you click on the export file, you will see you will get an Excel or a CSV file here, whichever one you prefer, and the entire content of this form will be saved on your laptop. So now if you click on paste from clipboard, you will see the new values have been entered here. There is no need to update those values. Once they're pasted, they are automatically saved. There are 3 more tabs. Water demands. This is pretty much the same story. You can change the demands individually. For example, in the first week, You could assume that because of the weather forecast, these demands are not realistic, they're too high, or maybe they are too low. So you can click on, look at, for example, this block 333. It has a demand of 11.591. Let's just change it to demonstrate that this feature works. We're going to put 15 here, for example, and we're going to click on the update button. Inflows is the next step. You will not have to change this because these inflows that you see here are the 20 percentile inflows for all inflow nodes. 20 percentile being pulled from the database of 89 years. So this is the 20 percentile for the last week of June for all years. This is the 20 percentile for the first week of July for all years. And this node is the inflow into the Ghost Dam. The same was done for Jumping Pound Creek, Snake Creek, Elbow, Highwood Elbow, and this last inflow here, the first one in the list actually, is the Crawford Creek, which comes into the Bassano Dam, or just upstream of it. Finally, what you may be interested in changing are these diversion license constraints. Here are the licenses as they're used in the model for WID, for BRID, and for EID. Now, if you know how much water you already diverted from the beginning of the season until the day you're running the model, you can deduct that volume from the number that you see here, and you can update the license. However, I'm finding that the licenses are usually not a problem. What you can also do is if you click on edit, on the edit button here, you can also update the maximum instantaneous flow rate in your diversion canals. These are the canals at the headworks, right? And the canal numbers are here. Div 99, Div 425, those are canal numbers in the schematic. For example, BRID has a maximum flow limit of 52.9. We can assume that the regulator calls the manager of BRID one day and says you have to reduce your flow to 35 cubic meters per second maximum for the next 10 weeks. You can put 35 here, you can click on update. And now that you're ready to run, you can click on calculate including seasonal data. Once you get the results, there are two ways to look at them. One way is to look at this file which was downloaded on your laptop or PC. However, that's not a very productive way. You're getting a file, text file with two files actually, one with the ideal demands and the other one with simulated levels for all components. So each component has 10 columns. If you put it in a spreadsheet, you can analyze it. A better way to look at the results is to go back to our schematic. We can first look at this show flow feature. We have to select the scenario, the proper scenario that we were running, so we don't look at the wrong thing. This seasonal operation scenario starts in 2021 at the 24th of June, so that's correct. And now we can actually adopt this default option, which is from the start to the end of the simulation. If we click on apply, we'll get the average flow for the whole 10 weeks. But it's more interesting to look at each individual week here. So starting on June 24th, our week is going to end on July 1st. And if you click on apply, you're going to get flows shown and the reservoir level, starting level, ending level, and net evaporation for this particular week. You can see local inflow, local runoff here. You can see water uses. For example, remember the block 333 that was right here. We set the demand to 15 cubic meters per second, and here is 15. That's this block 333. We don't, if you don't remember that, if you don't know the name of the block or the number of the block, you can click on show all names, and these are the component names. By the way, it's easy to change these component names if you don't like what we have set up here, but here is block 333 and it's receiving 15 cubic meters per second. The other feature you can check is this particular channel. Apparently, in the first week, there was no need to reach all the way to 35 cubic meters per second. 27 was enough. Was it like that for other weeks? Well, let's take a look. We can click on this chart option here. Again, select the same seasonal operation scenario and select the same channel, div channel 425. And we need to click on this add button to confirm that we're selecting from this scenario 425. And here we are. We have reached 35 cubic meters per second in the third week, and we stayed there almost until the end of the season, except for the last week. I'm talking season as being the 10 weeks that we ran. You can also look at this chart in another way if you'd like to see the histogram type of plot, because we're looking at average weekly flows. It's probably more politically correct because the flows are not changing the whole week, so they're staying at 27 and then about 32.48, and then they're up at 35 and staying at 35. So one more thing, if you go back to this feature and select McGregor Lake, again we need to go back to our operational scenario and reservoir 202. And then we're going to add two more things. There is the seasonal operation with demand increased. This is one of the scenarios we've created. Just have to make sure that we keep selecting the same component here, reservoir 2, and seasonal operation with demand decreased, reservoir 202. Again, we don't need the ideal because the ideal is already plotted for one of those, and the ideal level for the reservoirs in all three scenarios is the same. So once we have all of those, we can click on refresh chart and we see an interesting plot. This is what will happen to Lake McGregor in case we have predicted the conditions properly. Then it'll be the blue line. If we were off by 10% in either direction, up or down, in other words, being 10% more pessimistic or optimistic, the levels would look like this. And an interesting conclusion here is that the levels all end up at the same point after 10 weeks, which is the advantage of using optimization. Also, there are no deficits in these runs. In the entire 89-year simulation run has only a few years of small deficits for WID because it has no storage. But these are minuscule compared to what I had been seeing before. And also there are no deficits at all for BRID and EID. So this is about all I had to tell you for now. Thank you for your attention. And there will be other instructional videos outlining how to set up a project from scratch by yourself. Thank you.